out of nowhere.
Okay, give me, oh, sorry guys, give me just 1 second.
It is one of the fundamentals.
All right, Kitty, you gotta move, Kitty. I know, I love you. You gotta move. Alrighty, gang, welcome back. Today's our last day at MAP2302 differential equations, which is, slightly sad thing, but also quite happy thing. So it's with mixed feelings that I tell you, it's been a wonderful semester, and I really appreciate the hard work you guys have put in. Today, we are going to wrap up our discussion on power series solutions of differential equations by talking about solutions where the power series is centered at a singular point for the ODE. This presents some challenges, and I'm going to try to explain to you a little bit kind of the origin of those challenges rather than just being like, here's the algorithm, because, that never really helps us understand why we're doing what we're doing. There are a lot of reasons you might want to solve a differential equation with a power series centered at a singular point rather than at an ordinary point. Most significantly, remember that the convergence, when people use power series in practice, like when you're trying to solve a real world problem, a physics problem or something like that using a power series, you don't use the whole series. You use as many terms as you need to get within the acceptable error. And that error is a function not only of the number of terms you use, but kind of how far your interesting inputs are from the center of your series. So if I'm using 10 terms in a power series to approximate some solution function, but the x values or t values I want to plug in are like way over here, far away from my center, then even with 10 terms, that error is going to be pretty big. And sure, I could use more terms. I could use 100 terms or 200 terms, but that gets computationally expensive. And especially in the setting where you kind of want to take the next theoretical step using a truncated power series. This is something you guys, if you've taken physics 1, you've done, right? When you cook up the equations for a pendulum, you approximate sine theta, the angle, as just theta, and then you proceed to derive other things from that. Of course, that's using the first 2 terms of the power series expansion for sine, which is sine theta equals 0 plus theta. That's the order 1, n equals 0, n equals 1 terms. That works fine as long as theta is small, right? As long as the variable stays very, very close to the center. If you let the pendulum swing quite large, shit gets out of whack, and then all the mathematics you derive from that isn't useful. So in some situations, especially if you intend to take the theoretical work a little bit further after your power series, you don't want to use a bunch of terms, right? You want to use as few terms as possible in order to make the theoretical work that follows as simple as possible. Which means that the desired inputs need to be close to the center. And often, the desired inputs for your differential equation are quite close to a singular point for the differential equation. So you want to be able to center your series at a singular point. So that's the why. We're going to do the normal things here. MAP2302, just differential equations. And today is the 5th. I am going to go let my cat out. She's being quite needy. Okay, come in. Yeah, so that's part of the why, right? That's why do I even care about solving a differential equation about a singular point? Then there's the procedure, and there's the why associated with the procedure, right? So why is it that we need to do the thing that we need to do? Let me kind of remind you the framework that we're in here. So today, talking about series solutions centered at singular points. And the basic situation, you've got y double prime plus p of x times y prime plus q of x times y equals something. And you have a regular singular point about which you want to center your power series solution. Remember what a regular singular point is. It's a place that is at most an order 1 pole for P and at most an order 2 pole for Q, meaning a regular singular point. X equals x naught is 1, such that, when I say 1, I mean it's a singular point, such that x minus x naught times p of x and x minus x naught squared times q of x are analytic. Right, so in order for it to be a singular point, we need P and Q themselves, or one of P or Q, to not be analytic at x equals x naught. And then we call that a regular singular point if when you multiply it by x minus x naught, P becomes analytic, and multiply by x minus x naught squared, Q becomes analytic. And sort of the idea is because P is attached to the y prime and Q is attached to the y. How can I make this clear? Remember that taking derivatives of something, so just an aside. So a little bit of what's going on in the background. Consider the function y equals 1 over x. You know that y prime is negative 1 over x squared, right? So kind of, if I wanted to make this guy analytic, I would have to multiply by x squared. If I want to make this guy analytic, I would have to multiply by x. So kind of, if you imagine your solution function as having some problem at x naught, in this case at 0, the q of x, in order to clean things up, right? Imagine q of x has a problem at 0 also, and 1 over x is, for whatever reason, the solution to your differential equation. Then this guy, say q of x is like 1 over x. Yeah, so q over x is 1 over x and y is 1 over x. Then in order to make this whole chunk here analytic, you would have to multiply by x minus x naught squared. Right? Even though q of x only has an order 1 pole, if your solution also has an order 1 pole, then in order to make things nice, you would need to put together an order 2 pole. Y prime here is negative 1 over x squared, so this guy would be even gnarlier. So p of x can't be as bad as q of x. That's the idea, right? Is that if y has a pole of some order, then y prime has most likely a pole of even higher order. So this term is more likely to be problematic than this term. So in order to guarantee that things are sufficiently nice, the function p can't be as fucked up as the function q. So p needs to be fixable by a linear term, and q can be fixable by a quadratic term. I hope that this kind of makes sense. So p of x times y prime plus q of x times y would be p of x times negative 1 over x squared plus q of x times 1 over x. If we want these to be, we want this expression to be nice, then P of X needs to be at least one order less bad than Q. Right? If P and Q both have problems at 0, P's problem is, say P and Q have problems of the same order at 0, then this term is going to be one nastier than this term. Does that make sense? So if P had a pole of order 1 at 0, meaning like P has a factor of X downstairs, and Q has a pole of order 1 at 0, meaning Q has an X downstairs, then this would have an X cubed downstairs, and this would have an X squared downstairs. This one would be kind of one order pole higher. So in order for this expression to be nice, P of X must be, what's the right way to say this? One order less fucked than Q. I know this is not at all formal, but I'm just trying to help you see what's going on. So if your solution function has an issue at 0, say, and P and Q both have issues at 0, then in order for this expression to be no worse than this expression, P's problem at 0 has to be kind of one order less than Q's problem at 0. That's the idea. That's the kind of very basic idea of what's going on. So in order to call a point a regular singular point, I need to know that the problem here is at most of order 1, and the problem here is at most of order 2. All right. Now remember, I showed you Laurent series last time. Laurent series have terms in them like 1 over x, 1 over x squared, 1 over x cubed, and so on. Those are the problem terms. And what we want to do is kind of, in essence, we're going to assume that our series, the original series, the series for your function sort of without any corrective terms, is a Laurent series with finitely many negative index terms, meaning that you can multiply by some polynomial to turn it into a power series, or maybe not polynomial, some power function to turn it into a power series. So in words, that's what we're doing, right? Where you're assuming that the sort of natural solution function maybe has some issues, but those issues can be corrected by multiplying by a chunk like this. In the same way that I could correct the issue here at 0 by multiplying through by x squared, right? If I multiply x squared times this guy, then he no longer has a problem at 0. That's really what we're saying here and here. And so here's the theorem. Here's the mathematics behind what we're just saying. If x equals x naught is a regular singular point, then we can assume there is a solution to this differential equation, to 1 of the form y equals, instead, so normally we would just say some power series, right? Some sum n from 0 to infinity, cn x minus x naught to the n. But here we're going to throw in a factor of x minus x naught to some power, because maybe the solution actually isn't a power series. Right? Maybe the solution itself isn't analytic at x naught, because the coefficient functions are not themselves analytic at x naught. Maybe the solution inherits the non-analyticity of the coefficients. If you have a function that is not analytic, but not too far from it, meaning its Laurent series has finitely many negative index terms, you can always make that into a power series by multiplying through by whatever the biggest power of the negative index terms are. right? In other words, you kind of multiply through by whatever is necessary to clear those denominators. Then this would be analytic. The catch is we don't know what R is. So where R, generally positive, is a constant, right? If R were negative, then that term would be making things worse. Constant, which we need to find. And that's it. That's it. That's the game. So you just modify your sort of regular power series approach with one of these terms, assuming that the solution function is sufficiently nice to be cleaned up by such a thing. And a worthwhile thing to note is that since this doesn't have any ends in it, it can come inside the series, giving me sigma n from 0 to infinity, x minus x naught to the n plus r. So from there, you proceed as we have been. You differentiate this, you build the ODE. You're going to end up having to do all the index shifting and term matching that we did before. But in addition to that, you're going to need to find this constant R, and that usually will come from something called the indicial, or I'm not sure how it's pronounced. I've only ever seen a word written. Also indicial, coming from indices equation. When you differentiate this piece, of course, you'll get bits with n's and r's in them floating around over here. Some of those terms you'll have to pull out in order to make your starting indices match. And those terms, we know from experience, will have to be set to 0. That's where you're going to get the little equation or equations that allow you to find r. So that's the vibe. That's the vibe. Let's go ahead and just try it, right? This, by the way, is called the method of Frobenius. So I was always taught that this whole thing that we've been doing is the method of Frobenius, but your book specifically calls this theorem Frobenius's theorem. Yeah, this is the big one, right? So if you've got a regular singular point and you want to try to solve your ODE with a power series, you just slap a plus r on the power of x, or the power of x minus your center. If you don't do that, then your coefficients all come out to 0. And you'll be like, what the fuck? Because there is no analytic solution. That's why you need to start by looking for singular points, right? You noticed even in those ODEs we solved yesterday and the day before, I didn't just dive in. I checked for singular points first, even though we were in a section of the book where I knew there wouldn't be any, because it's a habit you need to get into. So let's try it. Let's solve 3x y double prime plus y prime minus y equals 0. All right, this is not a constant coefficient equation. So truly none of our other methods will do the job here. It's a second order equation. It's got variable coefficients. Unless it's a Cauchy-Euler, we're pretty well in fucked, and this is not a Cauchy-Euler. So the game here is going to be to start looking for singular points. If I put this in standard form, that is y double prime plus 1 over 3xy prime minus 1 over 3xy equals 0. So p of x is 1 over 3x, which is also q of x. And that means, so x equals 0 is a singular point. And so if I multiply by x minus x naught, so I guess I'll call this x naught, right? Oh no, x equals x naught is the notation we've been using. So x equals 0, 0 is x naught. So if I multiply p of x by x minus x naught, that's x times p of x, that's just 3. And x squared times q of x is, oh sorry, 1/3. 1/3. And x squared times q of x is x over 3, which are both analytic. All right, this is a constant function. Constants are definitely analytic. And x squared times q of x is a linear function, which is, again, definitely analytic. They're both polynomials. Every polynomial is analytic. At 0, I guess I should be very specific here. At x equals 0. Okay, so x equals 0 is a regular singular point. So we can assume that a solution of the form y equals x minus 0 to the r times sigma n from 0 to infinity cn x minus 0 to the n exists. Of course, I wouldn't normally write those zeros. That's just x and, x to the r and x to the n. So when I put this in a more manageable form, that's cn times x to the n plus r. So I'm going to solve this differential equation with a series centered at the regular singular point 0. Everybody with me so far? Okay.
Professor, I have a question.
Yes, sure, go ahead.
How does x times p of x equal to 1/3?
P of
I
x
don't know
is
if I'm
1
missing.
over 3x, right?
Mm-hmm.
So if you multiply that by x, you get x over 3x, and the x is
Wouldn't you divide by x?
maybe here off to the side. So P of x is 1 over 3x. So x P of x is x times 1 over 3x, which is x over 3x, and cancel, and you get 1/3.
Okay, I see.
Yeah,
Sorry.
nothing too crazy. No, no worries. So that means we can assume a solution of this form exists, right? X minus x naught to the r times the regular series cn x minus x naught to the n. I'm centering at 0, so it's just x to the r out front and x to the n inside. X to the r times x to the n is x to the n plus r. Y prime then is sigma n from 0 to infinity. You still differentiate the same way. The power comes down, I'll write it in front of the cn, and you get x to the n plus r minus 1. And y double prime is going to be, sigma from 1. I guess that's a subtle thing, isn't it? Yeah, no, I should still be starting at 0. Sorry. We mentioned this. When you differentiate a power series, you bump the starting index up if and only if the original series has a constant term. Does this series have a constant term? The answer there actually depends on what r is, but we're assuming r is not 0. If r were 0, then this series would have a constant term, right? Let me go ahead and write out the first few terms of this series. This is C0 times x to the r plus C1 times x to the 1 plus r plus C2 times x to the 2 plus r, and so on. So every time you've seen me differentiate a power series, you've seen me bump the starting index. Here, because this series does not have a constant term, when you go to differentiate this term, you don't get 0, you get r times x to the r minus 1 times C0. So when we differentiate series like these, where there is no constant term, you don't bump the starting index. Starting index here is going to stay n equals 0. That's got some advantages. It's going to make part of our job easier. everybody understand why this is staying a 0? Okay. So it'll stay a 0 when I differentiate again. And now differentiating this, I get n plus r times n plus r minus 1 times cn x to the n plus r minus 2. So these are the things we'll use to build our ODE. I'm going to need to shift the powers, and then I'll pull out some terms if needed. And we'll move forwards like we were before. So let's do it. I'm going to build, and I get 0 is equal to 3x times y double prime. 3x times sigma n from 0 to infinity, n plus r, n plus r minus 1, cn x to the n plus r minus 2, plus y prime, which is plus sigma n from 0 to infinity, n plus r, cn x to the n plus r minus 1, minus 1 copy of y, minus sigma n from 0 to infinity, cn x to the n plus r. There are some nice things and some not so nice things about this. First, I'm going to bring the x inside here. We can bring the 3 into it, doesn't matter. And then I'll see what I need to do about these guys. Turns out there's a factor of x to the r that's going to come all the way out. So this will be sigma n from 0 to infinity, 3 n plus r, n plus r minus 1, cn x to the n plus r, and then I've got a minus 2 here, but I'm multiplying by x, so that's going to bump that up to a minus 1. And now that actually matches with this guy, plus sigma n from 0 to infinity, n plus r, cn x to the n plus r minus 1, and then minus sigma n from 0 to infinity, cn x to the n plus r. Kind of a sneaky move here. From the first 2 terms, I'm going to factor x to the r. Actually, I'm going to factor x to the r from the whole thing. So remember, x to the a plus b is the same as x to the a times x to the b. Just a little algebra rule. So this x to the n plus r minus 1 is x to the r times x to the n minus 1. This is also x to the r times x to the n minus 1. And this is x to the r times x to the n. Since x to the r doesn't have any n's in it, I can bring it all the way outside the series. All the way outside all 3 series. Each one of these kind of looks like this. Has x to the r plus stuff. I can factor an x to the r out of everything that looks like this. And that's what I'm going to do here. Now in the first 2 series, you notice that the starting indices match, the powers match, and when I factor out an x to the r, these will both become x to the n minus 1, x to the n minus 1. So I can go ahead and combine those first 2 series into a single series, sigma n from 0 to infinity, in parentheses. From the first series, I have 3 n plus r, n plus r minus 1, cn from the second series, I have n plus r cn, close big paren, x to the n minus 1. Yes, yeah, I fit in. So this is everything from the first two series after factoring out x to the r. From the third series, after I factor out x to the r, I'll just have minus sigma n from 0 to infinity. I can't combine him yet because the powers don't match, x to the n. So take a second, doing quite a bit here. Make sure you can see where everything is going and coming from. These terms go here. These terms go here. I factored x to the r out from all three series. That's out here. That gets rid of the plus r in the exponents and leaves me with x to the n from the third and x to the n minus 1 from the first and second, which I factor from the combined series and write here. Quite a lot, I know. You can think of it like I'm going to divide both sides by x to the r. This term is pretty much irrelevant. I don't give a shit about him. But what I need to do is combine these two series. One has an x to the n, the other one has an x to the n minus 1. So in the first series, I will let k be n minus 1. In the second series, I will let k just be n. When n is equal to 0 in the first series, since k is n minus 1, this would give me a -1 starting index. And over here, when n is equal to 0, k would be equal to 0. We saw the Laurent series the other day. A negative index in a power series is not necessarily a bad thing, but it's not a power series anymore. It's a Laurent series. But I'll show you how to handle it. We're just going to pull a term out. It just means that this one is going to have an extra term compared to this one. That extra term is going to be a 1 over x term. So when I do this combination, I'll get x to the r times. I don't want to take the extra step to write it out, but I guess I really should. Yeah, let's do it. It's going to take space, but otherwise I think you get a little lost. So this is k equals -1 to infinity, 3n plus r times n plus r minus 1 cn plus n plus r cn. Sorry, fuck. I'm thinking too hard about the Laurent series stuff. Let's get a fresh sheet on where we're going to need it. All right, so we're going to bump up. Those are the substitutions we're going to make. It's right here. Equals x to the r, big bracket, sigma k from -1 to infinity. Okay. If k is n minus 1, then n is k plus 1. So this is 3 times k plus 1 plus r times, this is really n plus r minus 1 is the same as n minus 1 plus r. So that's just k plus r. Cn is going to be ck plus 1. And then x to the, no, that's good, okay. And then here, plus n plus r, again, is k plus 1 plus r. And Cn is ck plus 1. I suppose I could factor those out. So we have this whole thing times x to the k. And then from the second series, we just have sigma k equals 0 to infinity ck x to the k. So there's the index shift. But this looks weird, right? This looks hella weird. And also it's not the same as this. Fun question, which one has the extra term? It's really this guy, right? This has everything from 0 up to infinity. This has everything from -1 up to infinity. So this guy, this first guy, has the extra term, which is the -1 term. So we're going to pull out the k equals -1 term, which is going to be a non-polynomial term because of the x to the k here. So this is technically a Laurent series inside here. When k is equal to -1, what do I get? That's 3 times -1 plus 1 is 0 plus r. So that's 3r. K plus r would be -1 plus r, or r minus 1. C, -1 plus 1 is C0. Plus, plus k plus 1 plus r. When k is -1, that's 0 plus r is just plus r C0 times x to the -1st power. And then what's left is sigma k from 0 to infinity. And the sigma k from 0 to infinity now matches the starting index of this term. So I'm going to put everything inside here. I'm also going to factor the ck plus 1 and try to combine the terms in here in this step. So maybe let's see what we get there. This might be best done on a separate sheet just to get it out of the way. Yeah, let me come back here and reuse this piece. So if I have, so this is an aside. If I have 3 times k plus 1 plus r times k plus r, ck plus 1 plus k plus 1 plus r times ck plus 1, and I factor out the ck plus 1, I'll have 3 times k plus 1 plus r times k plus r plus k plus 1 plus r times ck plus 1. And you notice a common factor of k plus 1 plus r also. So this is 3 times k plus 1 plus r times k plus r. And then what would this be? When you factor out the 3k plus 1 plus r, let me do this a little more carefully. I'll use some brackets. So I'm going to bring k plus 1 plus r out, and I'll bring it out on the right. So I'll have 3 times k plus r plus 1 times k plus 1 plus r times ck plus 1. You guys see it? When I factor this common term out, this becomes 3 times k plus r, and this becomes 1. So this is 3k plus 3r plus 1 times k plus 1 plus r times ck plus 1. Just algebra, but there's so many symbols here. It's worth kind of stepping aside and making sure we're good with it. So are we all good with these steps here? So that will be the contribution to the coefficients from the first piece here. So in here I will have this 3k plus 3r plus 1 times k plus 1 plus r times ck plus 1. And then from that, I'll subtract the terms from this series, which is just ck. And I'll have my x to the k here, and we close our big bracket. Whew. So, what needs to be true? If this whole apparatus is going to be 0, then first you could divide over by the x to the r. The x to the r isn't really consequential. Or you could say that the x to the r term as a power function could never be identically 0. But you will need this to be 0, and you will need these coefficients to be 0. So I'll kind of rewrite it without the big scary brackets, trying to clean this up as much as I can. There is a common factor of r in here. There is a common factor of C0 in here. So I can factor out C0r. And then what's left is r minus 1, 3. Thank you, babe. What will be left is this 3 times this r minus 1 plus this r, right? That's 3r minus 3. Is this supposed to be an r or 1? Oh, I'm doing myself. Let me double check. I want to make sure that this is supposed to be on r c naught and not a 1 c naught, because it's contradicting my notes. So three and plus 1 minus 1. Good, good, good. Oh, when I did my shift, did I miss a term here? So n plus r should become k plus 1 plus r. N plus r minus 1, that's n minus 1 plus r, should become k plus r. So what do we get here? 3k plus 3r plus 1. K plus 1 plus r. This is good. Ck plus 1 minus ck. So this matches here. I'm just a little bit concerned because I've got a difference of 1 r from what I had when I ran through this. So I'm looking for the error. Anybody see an algebra error? Let me go ahead and write down what I get when I factor this r out. Maybe I'm just psyching myself out. So I'd have 3 times r minus 1. Factored out the C0, and I'd have a plus r here. That's the x to the negative 1. And then we'd also have this piece matches. This is good. 3k plus 3r plus 1 times k plus 1 plus r. Ck plus 1 minus ck equals 0.
Professor,
You see
you're
it?
factoring out the r, so it should be a plus 1, not a plus r.
Oh, thank you. I know I'm all right. Thank you. Thank you. Of course. Of course. Of course. Of course. Thank you. Okay. Yes, we're factoring the r. Okay, so everything's Gucci. So we get C naught times r. And then here I'll have 3r minus 3 plus 1, which is 3r minus 2, not 4r minus 1, right, 4r minus 3, which is good, times x to the negative 1. And over here, I can rearrange this. But before I rearrange this, I'm going to take this guy and do something with it. So there's a few possibilities. Looking at the expression on the left here, C naught could be 0. That's possible. R could be 0, or 3r minus 2 could be 0. So from this, I get C naught equals 0, R equals 0, or 3r minus 2 equals 0, which would mean r is 2/3. 1 over x is never 0, right? You know what the graph of 1 over x looks like. So those are the only possibilities there. These two, each one of these, I will plug in here to get a different recurrence relation. If you plug in r equals 0, right, then this term drops out, this term drops out, and you get one particular recurrence relation. If you plug in r equals 2/3, then this becomes a 2, this is a 2/3, and you get a different recurrence relation. So you get two different recurrence relations, each one corresponding to a separate linearly independent solution. It's an order 1 recurrence relation, right? So we don't expect this to be something that splits up the way the order 2 recurrence relations we saw before. All right. If C naught were 0, because this is an order 1 recurrence relation, then that would say this thing is equal to 0, which would imply that C2 is 0. So all the other C's would be 0. This gives what's called the trivial solution to the differential equation. And then either of these will give a distinct linearly independent solution to the differential equation. So taking r equals 0 in this recurrence relation to we get 3k plus 1 times k plus 1 times ck plus 1 equals ck, which would mean ck plus 1 is equal to ck divided by 3k plus 1 times k plus 1. And just like we were doing yesterday, you can plug in some values for k here and try to sort out your first few coefficients. Let's go ahead and do that. This, by the way, so if I set, we need to type the name from here, what we said is that r times 3r minus 2 is equal to 0. This is called that initial equation. So the equation in terms of r's that you get after pulling things out and setting those terms to 0. Of course, the C0 equals 0 is inconsequential. X to the negative 1 equals 0 is never true. The remaining pieces are called the initial equation. And these are somewhat important in the solution process because those are what are going to give us our particular recurrence relations. And I think your homework specifically asks for this by name. So I just want to tell you what it is. Okay. So I'm going to go ahead and take r equals 0 and start plugging in some values for k. So when k is 0, I get C1 equals C0 over 3 times 0 plus 1 plus 1. So C1 is the same as C0. Taking k equal to 1, I get C2 is equal to C1 over 3 plus 1 is 4. 1 plus 1 is 2. So that's C0 over 4 times 2. Taking k equal to 2, I get C3 equals C2. 6 plus 1 is 7. Sorry, did I say 6? K, yeah, k equal to 2. 6 plus 1 is 7. Times 2 plus 1 is 3. And then C2 is known, that's C0 over 4 times 2, so that's C0 over 7 times 3 times 4 times 2. Making k to be 3, I get C4 equals C3 of 9 plus 1 is 10, times 3 plus 1 is 4. C3 is known, so that's going to be C0 over 10 times 4 times 7 times 3 times 4 times 2. Say here you get the first few terms of your one solution, right? I could write down now one of the solutions. Equals. I remember the form we're assuming the solution to be isn't Cn x to the n, right? It's not sigma Cn x to the n. It's sigma Cn x to the n plus r. But here r is 0. So let me write it like this. Sigma n from 0 to infinity Cn x to the n plus r. But here, in this particular case, I am taking r to be 0. So this first guy would just look like a regular power series. It would be C0 plus, and then C1 times x. C1 is just C0 though. Plus C2 x squared, which is C0 over 4 times 2. Plus C3 x cubed, which is C0 over 7 times 3 times 4 times 2. Times x cubed. And then there's this one more term here. Plus, next one down here. Plus C0 over 10 times 4 times 7 times 3 times 4 times 2 x to the 4, which would be here would be that y1 is C0 times 1 plus x plus 1 over 4 times 2x squared plus 1 over 7 times 3 times 4 times 2 x cubed plus 1 over 10 times 4 times 7 times 3 times 4 times 2 x to the 4. And so on. So you've got your fourth order approximation for the first series solution. And this one happens to be a regular power series. No weirdness, because here r was 0. Next, we go through the whole process with r equal to 2/3. Everybody comfy with what we did down here? If we needed more terms, we could get more terms. If you see a slick pattern in here, let me know, but nothing is jumping out at me right away. We could try to arrange these like 10 times, arrange these in order, but there's repeats. It's really not obvious what this product downstairs is besides stuff of the form 3k plus 1 times k plus 1. So then we take r equal to 2/3 and run through it again. You want me to grab him, baby? Sorry, guys, puppy's being a little crazy. Maxwell. Hello. I love you, girl. You're gonna hang out with me. I'm sorry. I'm sorry. It's okay. All right. So what recurrence relation do we get if we take R to be 2/3? We get 3K plus 3R is 3 times 2/3, which is just 2, plus 1, a minute, times K plus 1 plus 2/3 times CK plus 1 minus CK equals 0. So I'll just say equals CK. This is, of course, 3K plus 3. Here, 1 plus 2/3, 1 is 3/3, so that's K plus 5/3. Why not? We'll take the space, 3K plus 3 times K plus 5/3. CK plus 1 equals CK. And I'm thinking probably because of the way we're going to do these computations, it might be nice to write this as 3K plus 5 over 3. So this is 3 times K plus 1 times 3K plus 5 over 3. CK plus 1 equals CK, and we're in luck because the 3's cancel. So we're going to see that CK plus 1 is CK divided by K plus 1 times 3K plus 5. So the product downstairs in these are going to be similar to the downstairs products in the other coefficients. And again, we just do the thing, right? So when K is equal to 0, we're going to get C1 equals C0 over 1 times 5. When K is equal to 1, we're going to get C2 is equal to C1 over 2 times 8, which is the same as C0 over 2 times 8 times 1 times 5. I know the order there is silly, but just to kind of help us prove where things are coming from. You take K equal to 2, you're going to get C3 equals C2 over 3 times 11, which is the same as C0 over 3 times 11 times 2 times 8 times 1 times 5. And I'll do one more. When K is equal to 3, we get C4 is equal to C3 over 4 times 9 plus 5 is 14, which is C0 over 4 times 14 times 2 times 8 times 1 times 5. So our second solution, Y2, this one we have to be a little bit careful with. Remember, this is still sigma n from 0 to infinity, Cn x to the n plus r. But here r is not 0, r is 2/3. So what I would probably do here is say this is x to the r times sigma n from 0 to infinity, Cn x to the n, which is x to the 2/3 times C0 plus C1x plus C2x squared plus C3x cubed plus C4x to the 4 and so on, which is, I got this puppy, he's fucking crazy. You guys won't believe what's going on next to me, which is x to the 2/3 times C0 plus C0, I'll write it like this. 0 over 1 times 5x plus C0 over 2 times 8 times 1 times 5x squared, that's C2, plus C3 is C0 over this product, 3 times 11 times 2 times 8 times 1 times 5 x cubed plus, did I write C3? Sorry, C0, that is C3. C3 is 0 over this, plus C4 times x to the 4, and C4 is C0 divided by 4 times 14 times 3 times 11.
Professor, did you miss a few terms in the C4 from the C3?
Did I? Oh, the 3
The
times
3
11.
and the 11?
Yeah. I got them down here. I just didn't write them there. I'm sorry. Yeah, so 4 times 14 times 3 times 11 times 2 times 8 times 1 times 5. 4, 14, 3, 11, 2, 8, 1, 5. But I definitely did miss them up here at first. So let's slap them on there. Times x to the 4 and so on. Okay. So these are our solutions. Fourth order Taylor approximation is pretty good. It's not perfect, but it's pretty good. It'll get the job done, again, as long as you stay close to the center. And here we are centered at the singular point, x equals 0. Finding a full solution, it's not gonna happen. And you'll discover that that's pretty much the truth for like 99% of differential equations out there. We're lucky in that many situations can be modeled by constant coefficient linear equations, or at least we can come up with okay models using constant coefficient equations. But most of the time, you have to make a compromise somewhere. Either your physical situation, you make a compromise in the model, where you say something which isn't necessarily constant is constant, like pressure. Pressure isn't constant. You move around on the earth, different places have different barometric pressure. But if that's not super important to you, maybe you set the pressure to be constant. That lets you use a constant coefficient equation. On the other hand, if the things you're trying to model are not constant and you refuse to sacrifice that, then you end up with a non-constant coefficient differential equation. And now you can't get an exact solution. You have to sacrifice in this sense, where your solution is at best a power series that's as long as you want, right? As long as you're willing to make it, but you're not going to find a closed form for this power series. No way, Jose. So these are your two solutions to the differential equation, or at least the first few terms of the two power series which would solve this differential equation. I want to take a second and just ask if there are any steps we want to go back and revisit. Maxwell puppy, you got to chill, bud. Maxie. So I know this was quite a lot. We can go back and look at any one of those series manipulations. We can talk about why differentiating did or did not change the starting index. We can talk about where the initial equation comes from. Any of that stuff. What feels spooky?
So we can use this theorem as long as there is a regular singular point for the ODE.
You can use this theorem anytime you're trying to solve a differential equation centering your series at a regular singular point. So, I mean, what I would usually do, what most people would usually do is center their series at an ordinary point, right? Stay away from singular points altogether. Singular points are a pain in the ass. But series that aren't centered at 0 are also a pain in the ass. So if 0 is a singular point, then I would consider using this theorem to solve about that singular point. Irregular singular points, no dice. Got to be a regular singular point. But yep, yeah, this theorem guarantees the existence of a series solution about a regular singular point. But I would consider, and if you're out there in the wild, I would consider solving about an ordinary point first, rather than going for a singular point. If you can, do that. Is that a satisfying answer to the question? I'm not sure.
Yeah, but what would happen if you try to solve it around the ordinary point, but x is equal to 0 is this regular singular point? Would it come out messed up or?
No, not a problem. So remember our theorem from last time said that the minimal radius of convergence for your solution about any ordinary point is the distance to the nearest singular point. So the equations we solved last time also had singular points. We just didn't use those for our center. Like we solved an equation last time that had a singular point at 1 plus I, or was it 1 plus 2I?
Yeah,
So that didn't hurt us. The fact that that equation had a singular point didn't cause me any strife. It just kind of limits the radius of convergence. That's
okay,
all. So it says
awesome,
that
thank you.
series will work, but it'll only work out to so far. It's only guaranteed to work out to so far. Other questions or comments, other stuff we want to look at here? I'll tell you, there's a hidden thing going on here. With the discussion last time, I was able to guarantee you a certain radius of convergence. Here, I can't guarantee you any particular radius of convergence. I can tell you that there is a positive radius of convergence. It's not 0. These series will converge on some open intervals centered at that singular point x naught, in this case centered at 0. And if you look at the example of this equation, these denominators are getting quite large. So the radius of convergence for this series may well be infinite. For both of these series may well be infinite. I suspect it is. But the theorem doesn't guarantee it in the way the other theorem does. So that's kind of another nice thing about solving about ordinary points rather than solving about singular points. Solving about ordinary points, you're guaranteed a minimal radius of convergence. Here, you're just guaranteed a non-zero radius of convergence. Back in the pen, Maxie. Maxie, come here. Yes, you're great. Love. All right. You guys got another one in you? These being the last few minutes of our last meeting, I'm inclined to kind of give you some choice. Would we like to do another solution about a singular point using power series, or is there something else you guys would particularly like to see right now?
Just a quick question. Are you having office hours today?
I will, yes. Today I'll have my normal office hour. Yesterday I had that doctor's appointment, but today we're good. Tell you what, if you guys want, so I'm looking at the problems in your textbook now. We could grab one of these as a problem to do as an example, or we could do something else like try to solve a Cauchy-Euler equation as an example. I've been told that Cauchy-Euler equations are great examples of solutions about singular points, but I haven't actually done one myself. So that might be fun. Yeah, none of these are Cauchy-Euler. Oh, let's see. If they don't include any in here as exercises, let me just. Let's see. Are these manageable? I think this would be a fun example because we'd also get a power series for sine cos log x, which could be a lot of fun. Nothing here. Yeah, maybe best we don't try to experiment live. Let me, oh, wait, here we go. Cauchy-Euler equations, that's it. Here's your method of Frobenius. equations. That might be fun. It's a regular singular point, so we could solve about that. And we already know these. Yeah, these turn out to be special functions. That's right. These are pretty nasty. Maybe it's best to take a look at one of the problems from your textbook as a wrap up. So last call. Anything that you guys would like to see from the homework or elsewhere before I dig into this last example for us for the semester? Okay, then here we go. We are going to solve the equation 2xy double prime plus 5y prime plus xy equals 0 about x equals 0, which I will just tell you is a regular singular point of this equation. You can verify, P of x is 2 over 5x and Q of x is 1/2. Q of x is on its own analytic, and P of x becomes analytic when you multiply by x. So x equals 0, I'll write them down. P of x is 5 over 2x. So x, P of x is 5x over 2x, which is 5 pounds, which is analytic at x equals 0. And x squared, Q of x, is, so Q of x itself is just 1/2. So this is x squared times 1/2, which is also x equals 0. So x equals 0 is a regular singular point. It's a singular point, of course, because P of x on its own is 5 over x, which has a pole of order 1 at x equals 0. So I am going to assume that y is of the form sigma n from 0 to infinity Cn x to the n plus r, which means y prime is going to be of the form sigma n from 0 to infinity n plus r Cn x to the n plus r minus 1. Y prime prime is sigma n from 0 to infinity n plus r times n plus r minus 1 times Cn x to the n plus r minus 2. And then we'll build the ODE, factor out x to the r, combine our series, pull out terms, solve the initial equation, find our recursions, 2 of them, each corresponding to the various values of r, and then find the coefficients. So now we build. I have 2x times, so 0 is equal to 2x times y double prime, which is this guy. Plus 5 times y prime. I suppose if there's a catch here that you need to be careful about remembering, it's that when you're not using the Frobenius method, when you're not having the r terms in here, you would bump the indices when you differentiate. But when you do have the r in there, you need to remember not to bump that. That's a place where I know people get into trouble in Calc 2, and I want to remind you to do that here. But to do it in the other setting, where your series really does start with a constant. And then we have plus x times y. can bring in the x here and here. Where are the twos and stuff also? So it's 0 to infinity, 2 times n plus r times n plus r minus 1, cn x to the n plus r minus 1. N plus r minus 2, I multiply by x to the 1, the power goes up by 1. Plus sigma n from 0 to infinity, n plus r, cn x to the n plus r minus 1. So that's nice, those match. But this guy is going to be way off. He's going to be plus sigma n from 0 to infinity, cn x to the n plus r plus 1. So there's a gap of 2. In this guy, I'll substitute k equals n plus r plus 1. And in both of these, I'll substitute k equals n plus r minus 1. Oh, shit. All right. So let's get some of the algebra out of the way. And no, the algebra will be easier after we clean things up, right? Like, so what's this up here? K equals n plus r minus 1. So this will be k. Yeah, it'll be easier after we clean things, after we make the sub. So the first two get the sub, k equals n plus r minus 1. And this guy gets the sub, k equals n plus r plus 1. I know I need to factor the x plus r out before I can even do that. Yeah, so never mind. It would be easier to do the algebra with these bits, but so let's bring the x to the r out now. I'll leave them separate. 2 times n plus r times plus r minus 1, and then here this will just be x to the n minus 1. Yeah, we're not that lucky, are we? Plus sigma n equals 0 to infinity. Plus r. Oh, I left my cn here, didn't I? Plus r cn x to the n minus 1 plus sigma n 0 to infinity. Yeah, x to the n plus 1. All right. Now this first one, first two, I let k be n minus 1. And this one I let k be plus 1. When n is 0 in this guy, k is -1, and the same is true here. And this guy, when n is 0, k is +1. So I'll get x to the r sigma k from -1 to infinity. N is k plus 1, so this is 2 times k plus 1 plus r times n minus 1 plus r is k plus r times c k plus 1 x to the k plus sigma k from -1 to infinity 5 times k plus 1 plus r times ck plus 1 x to the k plus this guy got the different substitution when n is 0 here, k is equal to 1. Cn would be ck minus 1. X to the n plus 1 is x to the k. So there's the substitutions. Index shifts. The first two series are easy to combine. We should combine them. and then we'll do whatever work is necessary to combine the resulting series with the third. So I've got a ck plus 1 x to the k that will come out, and then I've got k plus 1 plus r, k plus 1 plus r common factors. So I can bring all that out, not out of the series, but out of the coefficient one. Sigma k from -1 to infinity k. Big parentheses. I'm going to factor out the following pieces when I combine these two series. I'm going to factor out this. Factor out these. So what I'll have left is 2k plus r plus 5 and then k plus 1 plus r, and then ck plus 1 x to the k. All right, that's those first two series combined. And then I have in my second series here the sum from +1 to infinity c sub k minus 1 x to the k. All right, so these two series come together into one series. Within that one series, I can factor the common terms, which are the blue underlined terms. When you factor out the blue underlined terms, what's left is 2 times k plus r plus 5. That's exactly what you see here. So that's 2k plus 2r plus 5 times k plus 1 plus r. And then you notice that this term, or this series, going from -1 to positive infinity, has the -1 and the 0 term that this series doesn't have. So we need to pull out k equals -1 from this and k equals 0 from this. I'll do my best to make it pretty. So when k is -1, this is 2 times -1 plus r plus 5 times -1 plus 1 plus r is just r. Puppy, hey. Eating paper crane, puppy. All right, times -1 plus 1 plus r is just r. C -1 plus 1 is C0. And x to the -1 is x to the -1. Then to that, we have to add the k equals 0 term, which is 2r plus 5 times 1 plus r times C1 x. We'll do plus ... plus this series, but now starting at 1, which I can combine with this series. So that is sigma k from 1 to infinity. I might as well go ahead and distribute that 2, right? So that's 2k plus 2r plus 5 times, I'll write it as k plus r plus 1 times ck plus 1. This minus ck minus 1 times x to the k. And let me turn this into a curly brace. Close the curly brace. All right. Pretty severe looking expression, but all the same stuff's going on here that went on before. I'm going to set this term to 0 set this term to 0, set this stuff to 0. Therefore, that's -2 plus 2r plus 5. -2 plus 5 is 3. So that's 3 plus 2r times r equals 0 from the first guy, from this very first piece. And then we have 2r plus 5 times 1 plus r equals 0. So this is really my initial equation. And then this I can think of as a consequence of the recursion relation. But let's go ahead and write it down. 2r plus 5 times 1 plus r times c1 equals 0. I'm including the c1 there because, again, the recurrence relation should take care of this. And my recurrence relation, which is 2k plus 2r plus 5 times k plus r plus 1 times ck plus 1 equals ck minus 1. In other words, ck plus 1 equals ck minus 1 divided by 2k plus 2r plus 5 times k plus r plus 1. So the bottom right is my recurrence relation. I'm going to get a couple values of r from this. I could solve for r here as well, which would give me a total of 4 values for r. And I'm going to have to think a little bit carefully about what to do with this. My initial feeling here is that this guy, this term coming out to 0, because it comes from the same terms of the series here, should be handled by the recurrence relation. I don't believe the -5/2 or -1 values of r that you could get from this are actually relevant to the problem. I think just these are. But we can check. So the first thing to do would be to take the 2 values of r you get from this, plug them in here, start crunching away your solutions. You should only have 2 linearly independent solutions because it's a second order equation. So either the solutions you get from this would be dependent or would actually be contained, would be redundant, would actually be contained within the stuff you get from the 2 original r values in your recurrence relation. I suppose if we wanted to get around that issue, one way to do it, yeah, actually, this is how I know you don't need this. You ready? Instead of bumping this all the way up to k equals 1, I could have bumped this down to 0 and this up to 1. Sorry, and this up to 0. That would be another way to resolve this without pulling out 2 terms. And then the terms associated with this would just be contained within the recurrence relation. So this is my initial equation. And from that, we get r equals 0 and r equals -3/2. If I take r equal to 0, then my recurrence relation becomes ck plus 1 equals ck minus 1 divided by 2k plus 5 times k plus 1.
Wait, shouldn't the ck minus 1 be negative?
So this was a difference, right? This minus this equals 0. So when I set this all equal to 0, I just add ck minus 1 to both sides. So now this should be positive. That part is correct.
But above that, it's plus CK minus 1.
Say that one more time.
But above that, in the series of
Oh,
CK, plus CK
yeah,
minus
yeah,
1.
yeah. Looking two up. I see. Yeah, looking two up. Make sure. Yep, this should be a plus. So this should be a plus. So this should be minus. So this should be minus. Thank you. Yeah, you're correct. You're correct. Very good. Okay. So taking R to be 0, we get this. And then I can start plugging in some Ks. If I plug in K equals 0 here, I get C1. And then over here, I'll get C negative 1. I don't know anything about the negative indexed values there, but let's just write it down. K equals 0. And let's see, C1 equals negative C negative 1 over 2K, 2 times, sorry, 0. Yeah, 2 times 0 plus 5, which is 7. 0 plus 1, which is 1. But maybe this is a place where we could use this second kind of initial equation we get, where here we would say, all right, well, I could take R to be negative 5 halves, negative 1, or C1 equal to 0. So we could maybe say from this that C1 should be 0. Because here, we don't know anything about this guy. We don't know what this even means. But C1 equals 0 by star. Question mark. We'll just type that in our pocket. When we take K to be 1, we will get C2 equals negative C0 over 2 plus 5, which is, I took K to be 0 here, didn't I, too? Yeah, sorry. So this would just be a 5 minus 7. Okay. And now here we'll have a 7 times 1 plus 1 is 2. And C0 we know is going to be one of our free constants. So I can just leave it like this. When I take K to be 2, I'll get C3 is equal to a negative of C1 over 2 times 2, which is 4, plus 5 is 9, times 2 plus 1, which is 3. And I could say that this is 0 based on star. But for now, I'll just leave it like this and see if we do get a second solution here. So I think what it's looking like, and this is not what I expected, what it's looking like is that the C1 equals 0 from this is going to kill half of the terms from the R equals 0 recursion, which is a good thing, really, because this is an order 2 recursion. The gap between CK plus 1 and CK minus 1 is 2 rather than 1. So if we didn't have something to kill half the terms here, we would end up with a split. Again, I'll say maybe this should be 0. 5 star. But I'll continue writing the terms that depend on C1 just in case for some reason it becomes relevant elsewhere. If we take K equals 3, we get C4 equals negative C2 over K is 3 here, so this is 6 plus 5, which is 11, times 3 plus 1, which is 4. And then C2 is known. C2 is negative C0 over 7 times 2. So the two negatives would eat each other up, and I would get positive C0 over 11 times 4 times 7 times 2. Since several of these were 0, let me go ahead and take 1 or 2 more. C5 would be negative C3 over 10 plus 5 is 15 times 5 plus 1 is 6. But C3 we conjectured is 0. minus 1. When I take k to be 5, I get C6 equals negative C4 over. Yeah, this shouldn't be a 15, should it? This is k equals 4, so that's 8 plus 1. This one would have to 15 and 8 plus 5 is 6. And so that's C4. That's C0 of 11 plus 4 plus 1 plus 2. And that was positive, so this is going to stay negative, so it's negative C0 over 15 times 6 times 11 times 4 times 7 times 2. All right, so now we do have some non-zero terms here that we can play with. 1, 2, 3 non-zero terms. All the way up to the order 6 stuff. I'm pretty happy with that. So we can say one of our solutions, y1, this is the one associated with r equals 0. Sigma n from 0 to infinity, cn x to the n plus r, 0 would be 0 plus c1 x plus c2 x squared plus c3 x cubed. Would be c0 plus c1 is 0, c2 is negative c0 over 7 times 2, so we will minus c0 over 7 times 2 x squared. C3 is 0. And then next we have C4, which is plus C0 over 11 times 4 plus 7 times 2 x plus 4. C5 is 0. C6 will be minus C0 over 15 over 6. 11, 4, 7 times 2, x to the 6. So there's our 6th order approximation for that first function. Appears to be an even function. It's interesting. I am a little bit wondering if we're losing information from that, assuming that C1 is 0, but it doesn't appear that we are. I think that this is probably kosher. And then we would get our second solution by doing the same thing, but with r equal to negative 3 halves. Yeah, negative 3 halves. So our second solution, r to be negative 3 halves in here. What are we going to get? Good. Maybe it'd be easier to look at it up here first. So r is negative 3 halves. We'll have 2k. And then plus 2 times negative 3 halves is minus 3 plus 5 times k plus r plus 1 is k minus 3 halves plus 1 times ck plus 1 equals negative ck minus 1. This is 2k minus 3 plus 5 is 2k plus 2. And this piece here, this would be 2k minus 3, 2k, and then minus 3 halves plus 2 halves is minus 3 plus 2 plus 1. Minus 1 all over 2. And again, we'll be able to factor and cancel the 2. So this is the same as k plus 1 times 2k minus 1 ck plus 1 equals negative ck minus 1. So finally, And putting that into the useful form of ck plus 1 equals negative ck minus 1 divided by k plus 1 times 2k minus 1. We can start plugging in values for k. When k is equal to 0, again, we have this weird business here, but we know that C1 is supposed to be 0. So let me start with k equals 1. And then we'll get C2 is equal to the negative of C0 divided by k is equal to 1 here. So this is going to be 2 times 1. When k is equal to 2, we're going to get C3 is equal to the negative of C1. Well, 2 plus 1 is 3. And then 1 minus 1, that's also 3. So this would be 0 by the assumption that C1 is 0. K is equal to 3. We get C4 is equal to a negative of C2 divided by 3 plus 1 is 4 times 2 times 3 is 6 minus 1 is 5. And then we know what C2 is. That's negative C naught over 2 times 1. So this would be positive C naught over 4 times 5 times 2 times 1. I take k to be 4. We're going to get C3. It's going to depend on, sorry, we're going to get C5. It's going to depend on negative C3 over, who cares? That's going to be 0. And take k equals 5. We get C6 is negative C4 over k equals 5. Yes, C6 is equal to negative C4 over 5 plus 1 is 6 times 2 times 5 is 10 minus 1 is 9. C4 we know, so this will be negative C naught over 6 times 9 times 4 times 5 times 2 times 1. And again, I've got the first few non-zero terms. It's like this is also an even function, but with different coefficients. So y2 would be x to the negative 3 halves times C0 plus C1 is 0 minus C0 over 2 times 1 x squared plus C0 over 4 times 5 times 2 times 1 x to the 4 minus C0 over 6 times 9 times 4 times 5 times 2 times 1 x to the 6 and plus and so on. So these would be our two solutions. Second order equation, two solutions. As long as they're linearly independent, then we know that they are indeed all of the solutions. Just for fun, let's see what a computer algebra system does with this. A little bit over time here, appreciate your patience. All right, so I claim that the two solutions to this differential equation are this guy. Is that y2 for that one, or is that a different equation? This guy. One of them. And the other one that we came up with here. Let's see how we did. So our ODE here was 2xy double prime, right? with y double prime. Yeah, plus 5y prime. Plus xy equals 0. Let's see what sort of series solutions Wolfram spits out. Those are Bessel functions, the J functions. Strong-Liouville equation. It's all going in terms of Bessel functions. No dice. All right, sorry guys. Series solutions. Nah, won't do it. That's okay. So the result here in terms of Bessel functions is kind of neat. Bessel functions aren't something that we know anything about though, so I can't really share that with you, but these are the two solutions that we come up with. So that is the end of differential equations. You've made it through. The final exam will contain some power series stuff, but nothing super brutal. I'll break those problems down into bits. If I were to put a whole problem like this on the exam, of course, it would take the entire time for you to do it, and that would not be at all reasonable. But I might ask you to cook up the initial equation, or to classify points as ordinary, singular, regular singular, or irregular singular. And then I might give you something that's very simple, like a solution about an ordinary point, and just tell you to get to the recursion stage, something like that. Everything else is fair game on the test. Any Laplace transform stuff, any constant coefficient stuff, any first order stuff. That's about it. I'm going to go ahead and publish your take-home test, and then you guys are good to go. I'm trying to think if there's anything else that you need to know from me before I let you go. Take-home test will come out today. Study guide for the final will come out today, and that'll be it. You just want to spend your time between now and the final exam preparing for the final. Anything you guys would like to ask me before we wrap it up here?
Yes.
Sure.
Go ahead, sorry.
I just wanted to ask how many questions there would be in the final exam.
Not sure yet. Haven't written it. Usually, so for the classes like this, I'd do somewhere around 20 questions on the final. That won't be 20 differential equations you need to solve, though. That would be 20, like, you know, find the initial equation or describe the roots of the auxiliary polynomial, that sort of thing. So somewhere around 20, but yeah, I haven't written it just yet.
Is it going to be both multiple choice and free response, or?
Yes, it'll be the same
Okay.
structure as our midterms, just a little longer. Any other questions? Alrighty then, guys, I'm going to go ahead and end the meeting. I do have office hours today. If you want to talk about anything, watch for the take-home test on Canvas, and I'll post an announcement before the final with really detailed instructions, exactly what I need you to do on the day of the final. Also watch for the final exam study guide. All right, if you need anything from me, just let me know. Otherwise, I will see you guys on the day of the final.